You're on mute.
Okay, now I'm not on mute. But you do, yeah, so you do need somebody that you embrace consistency, or that you are consistent. And then the other side of the coin is between components of your system, you embrace that effectual consistency. So, if you're talking about messaging, messaging is basically all about getting stuff from here to there. And this is taken directly from a very smart guy, Clemens Fosters. If you don't follow him on Twitter, it's probably worth doing so. And it's basically all about taking the information from one place and moving it to another place. Sometimes there's a lot of here and only one there. Sometimes you send a lot of data, and sometimes there's a lot of there that you send it to. So depending on what you're trying to do with messaging, you're either sending from point to point, or from multiple points to a single point, or from a single point to multiple points, or a various combination of those. The points where you send in the information can also all be different. It's also important to note that sometimes the place where you send in the messages isn't there. So if you've got something that's supposed to respond to messages and it's not up and running, what do you do in that case? If it's super busy doing a whole lot of other stuff, what do you do in that case? And then if something goes wrong and the message physically doesn't get to there, what do you do in that case? And then if the endpoint is also broken, what happens to those messages? Okay, so it's all about sending messages from one place to another place. How you do that, how you go about making sure that those messages actually get there, that's up to you. And what happens if the system isn't available is also up to you. So messaging forms part of the typical application integration patterns. I don't know if you guys went through it directly in reading last time, but there's a whole lot of different ways that you can do application integration. And usually, it seems that we tend to default towards a shared database, except if we work in banks, and then we do file transfer because that's cool. I don't know why. If you are WCF, you are more than likely doing RPC, or remote procedure call. You don't have to with WCF, but typically the examples that you see kind of lend you or with WCF. And then you've got messaging, which can also do it as an RPC type approach, which you really shouldn't. So if you've got all these, and I'm sure there's other ways of doing integration as well, but if you've got these different ways of integrating different system components together, how do you actually go about and choose which one is appropriate for your system? So there's got to be some type of mechanism that makes sense. And yes. So if you've got these various different approaches, there's going to be some type of evaluation criteria to choose which one is most appropriate. And thankfully there is. So if I stick these out to the side, there's a couple of things you need to consider. So first of all, do you actually need to integrate with consistent components? So is the system you're working on of sufficient scale to warrant putting different components in different places and having some type of communication and integration? If it isn't, guess what? Your problem solved, and just do it all in one episode. Is there any kind of coupling between the different pieces of the application? And what type of coupling is it? Is it a tightly coupled system, or is it merely highly cohesive? So what are the bits and pieces that have to be shared across the system? If you change, for instance, your database in one portion, is it going to affect every whether you're doing something FTP, the file transfer? How simple is the integration that you need to do? This is a bit of it's a duck because it's a duck kind of thing, so how simple is integration? It's as simple as you make it. But can you get away with just doing a file transfer? Does it make sense to just do a shared database? Do you actually have to go and do a messy system? There's sometimes criteria that impacts that decision. Are there technology constraints that you have to work around? So if you're in a banking environment, Are you allowed to use RabbitMQ? Are you allowed to use Oracle database? Or are you forced to use Oracle database? So all of that's going to guide whether or not, or which approach you could use. Is the data format, or do you have to subscribe to a particular data format or something integrated? So again, a lot of these examples are going back to the banks because they do tend to have a lot of these systems where you have to have the format of files in a particular way. And then if you're doing something like SOAP integration, so if you're doing the data power or WCF services, again, you have a particular contract you have to conform to. What is the level of scalability? A word, can we make it a word now? How stale can the data be, or the messages, or the integration between the different systems be? And this is an important concept because I don't think it's questioned often enough. So if you talk to a user, users going to say, no, I must have the most up-to-date information that's good. Why am I building this computer system if it's not up to date? Why am I paying 3 million rand to get a system done if I'm not going to get any real-time data? But that's a complete lie. There's no such thing as real-time data. So even if you take a desktop application that's connected directly to the database, by virtue of the fact that you are sending electrons over the wire to actually communicate, by the time the data gets on the screen, there is a level of staleness to that data. Whether or not that impacts the user, that's the important part. So determining what the level of scalability, I'm going to use that more often now, the staleness, damn it. Determining the level of staleness that your users can accept. Damn it. Determine the level of staleness that your users can live with is important, especially when you do try and embrace things like event consistency. A good example is ATMs. So if you go and draw money at an ATM, do you think your bank balance updates instantly? What if there's some communication failure between the ATM and the central bank? It's not going to immediately go and say, no, sorry, you can't draw money, because that's the worst case scenario. If an ATM denies you from drawing money, as far as the bank is concerned, that's even worse than then you draw too much money. You're now going to piss someone off who's going to go on Twitter and cause a whole war over the fact that they couldn't draw any money. So it's not that the ATM has to be real time, but it has to be close enough that it doesn't expose the bank to a major amount of loss. And it's difficult to convince clients of this, and I don't know how yet because I've lost every discussion around that. So, I don't know. And then another point that you have to consider is, are you sharing data or are you sharing functionality? So if you're sharing functionality, you're allowing people to invoke certain system calls within your application, maybe that would push you more towards an RPC type of integration. Or if you're sharing data, maybe file transfer is more appropriate. So there has to be some type of decision around what functionality or data you're sharing. And then the last one is obviously the last one that I'm going to cover is concurrency. So how many different users do you need to be able to access the system at one time? If they're accessing the same customer record at the same time, how do you deal with issues around them updating the same field or maybe even different parts of the same customer application, the same customer field? If you have to cater that scenario, something like a file transfer is going to be very difficult to actually get the integration working. Maybe messaging is a bit of an approach there, because you can say things like updated password as opposed to here's my new customer record. So you've got context around what's happened rather than just here's the data. So it's something you can use to guide what type of integration you're going to use. If we start doing distributed systems, and this is an actual thing, it's not something that I've come up with. I don't use the word fallacies in normal conversation very often, as much as I'd like to. I'm more of a scalability kind of guy. So this is a set of attributes that some dude in the 70s came up with, and it still seems to hold true today. And it's to do with what people assume when they're dealing with network systems or distributed systems. So people assume that the network is reliable, that latency is zero, bandwidth is infinite, the network is secure, topology doesn't change, there's one administrator, transport cost is zero, and the network is homogeneous. And it's not the case. We have a lot of the stuff that just works for us a lot of the time. So when you're connecting to a database, how many times do you put a try catch around the actual connection portion? It doesn't happen very often. If you connect into a REST service and you're using JavaScript, you might put a fail on the end of the promise, but that's kind of about as far as it might go, and it'll pop up an idle box saying, "Let's try again." So we tend to assume that things are just going to work, and it's not always guaranteed to be the case, especially when you are dealing with things like message systems. So keeping that in mind, if you want to actually visualize the way we do messaging systems, the way we integrate this stuff, it's maybe not a bad idea to picture yourself sitting in the trenches somewhere where you have to send a message to some other guy, and you're not actually sure if that message is going to get there. For instance, something could go wrong. You could have, I keep trying to say the word falcon. You could have a falcon designed to catch message pigeons. It could get lost. The message could completely get lost. The message itself could get garbled. That's not even that bad of a picture. Come on, guys. don't look at my Google history. So it's important to be aware that things do go wrong when you are dealing with distributed systems. It's not something you can just pretend and abstract away. Even if you are using something that guarantees reliable messaging, think about how they did that. What do you sacrifice in order to get that reliable messaging? So it's always kind of a good idea to picture yourself in the middle of some remote place where you have to get information to somewhere else, and just don't assume that it's magically going to get there. One of the more famous computer science problems is the Byzantine general problem, where with messaging, if two generals in a war are trying to send a message, how do they know if the message is actually going to get there so they can synchronize their attack on the place? And currently it's an unsolvable problem. So if you look at the concepts around messaging, you've got things like reliability. So how do you guarantee that a message is going to get there? Assuming it gets there, how do I make sure it only gets there once? Or how do I make sure it doesn't get there multiple times? So you've got at most once messaging, at least once messaging, and exactly once messaging. Most messaging systems that you work with are at least once messaging. So the message will get there. It's guaranteed to get there at some point, but it could get there 2, 3, 4, 5 times. And you need to be able to deal with getting that same message 5 times. At most once messaging, it'll never get there more than once, but it does also mean that it might not get there. Exactly once messaging means it will get there once and only once. You sacrifice a lot to get exactly once messaging. And usually, in fact, none of the big vendors promise exactly once messaging. It's usually layers around at least once messaging that keeps track of that, and then you eventually get to your exactly once messaging. Okay, and then you've got concurrency, which is important to do with messaging. So if you've got 5 messages that come through at the exact same time, all dealing with the same customer record, how do you deal with that? And this is usually handled by but on the same intent, whatever the change was. Open level. So something like if a customer's address changes, is the address changing because they've moved, or is it changing because you typed the wrong address the first time? So what is the intent behind that change? And if you represent the intent of the message you send in as well as the actual change that occurred, usually concurrency becomes less of an issue because there's not much chance that there's going to be 3 guys changing the same address because the guy moved at the same time. And then the big one is transaction scope. So if something goes wrong, how do you roll that back, or how do you do, they call it corrective actions, compensating actions. What compensating actions can you do? How do you roll that transaction back? Do you need distributed transactions? And this is, everyone says they need a distributed transaction, so if I can't build the credit card over there, everything must roll back to the same state before. I don't necessarily agree with that. but it's one of those things that I tend to lose the argument with as well, especially when clients are involved. Okay, so look at reliability. How do you achieve reliability within a messaging system? Again, this is not something you typically have to implement. Most of the time, this is done for you. But they might use concepts such as store and forward. So if you use an MSMQ and you're trying to send a message to a remote server, MSMQ under the covers will actually create a local queue, store the message locally, and once the server becomes available, it will send a message to that server. So you're guaranteed to eventually get there because you don't lose the message locally. Remote pull, if you're using any queue service that's atom-fronted, you'll be doing something like remote pull. A lot of the systems that do remote pull work utilize caching very extensively, so give me these records, oh, I've already got these 5, only give me the next 2 there. Of doing excuse me, has received what that happened. Two-phase transmission, very similar to two-phase commit. So if you're dealing with any database system, they will always have two-phase commit. They say, I'm going to write some data, I'm going to write some data, I'm going to write some data, here's the data, here's the data, here's the data. Okay, write the data, write the data, write the data. And you always prepare to say, I'm going to do something, you send the information, then once you send the information, you confirm that you sent the information. Databases use this extensively, and some messaging systems is, again, usually for at least once messaging. Transmission buffer padding. So instead of just sending the last message or the current message, send that one and maybe the last 5 messages as well at the same time. So if the client did perhaps miss one of the messages along the way, you know, there's high probability they're eventually going to get those messages. You're going to send a whole lot or a whole bunch at once. Again, not something you usually have to worry about, but those are some of the approaches some messaging systems use to achieve reliability. Message bus, so this is again just a cover the concept of a message bus. So a message bus is a common domain model. So if you hear people talking about a service bus, specifically an enterprise service bus, that is not this. This is a message bus. If you're dealing with in the .NET space end service bus is actually a message bus, not a service bus. So there is a big difference between a service bus and a message bus. A message bus is a common message platform, a common data model, common command set, common messaging infrastructure with a shared set of infrastructure. An enterprise service bus is, think of it like a highway with a whole lot of on-ramps and off-ramps where any system can get on and send any car on or any type of message on. And eventually you'll get to Pick and Pay or wherever you're trying to go. Where a message bus is, if you want to send a message, put it in this format. I know that when I get this message, it's going to go over here. So there's a difference between a message bus and a service bus. So we look at some of the patterns now, and the easiest one to look at is point-to-point messaging. So point-to-point, I'm hoping that is obvious. I have a message here, and I want to send it there. So what do? I send it there. Fairly straightforward, right? If I want to send a message to another place, hey, I do, because I can do that. It's point-to-point. Doesn't have to be clever. So this is probably the simplest form of messaging. If you dealing directly with, for instance, an MSMQ queue or RabbitMQ queue, and you've explicitly configured where the destination of the message must be, you're doing point-to-point messaging. Very simple. The downside is you have to know exactly where the consumer is. So you can do configuration around it. You can say, well, I'm going to put my endpoint in a config file for a database, or calculate it at runtime, or whatever. But at the point where you physically send the message, you have to know where the message is going. Okay? So that is going to have an impact on what, excuse me, on whether or not this is applicable. Question though is, what happens if the consumer is offline? Any takers? So yes, it depends on the underlying technology you're using to actually send that message. If you're using WCF and the consumer is offline, guess what? It's not going to get there. If you're using MSMQ, it'll do store and forward. If you're doing RabbitMQ, store and forward. So the underlying technology will leak up into the application layer at this point. And the decisions you make around the technology will have an impact on what happens to messages at this point when the consumer is offline. If the consumer is offline, do you also know that that message must go to that endpoint? So if you are using MSMQ, cool, the message will get to the destination you eventually set it to, but so there are kind of nuances around point-to-point messaging that you do need to be aware of, and you're not always guaranteed to have the same IP address when your machine logs on again. Okay, then we've got publish, subscribe, PubSub. I'm hoping everyone is familiar with this one as well. Backwards. So publish, subscribe says, okay, cool. Well, this has occurred. I want to send this message. No one's interested in it. Okay, I'm just going to lose this message now. Okay, if someone is interested in those types of messages, they will send a message to the publisher first to say, hey, when this type of message occurs, let me know about it. Or when this thing happens, tell me about it. So I'm subscribing to information about this event. It should actually be subscribe, publish, not PubSub. So then the publisher keeps a record of, okay, well, these are the people that are interested in this type of event. So if event T1 occurs, I need to send it to node B. So cool, that event occurs, we send it to node B. Node D then says, okay, I also want to know about event T1. So now the publisher at this stage has to keep track of two clients. So when an event T1 occurs, we send two messages. So everybody that's interested in that type of event receives a copy of the message. And it's up to the publisher to keep a record of who those messages must be sent to. Okay, so if the publisher comes down or goes down and comes back up, and you've just stored a list of the consumers in memory, well, the next time an event occurs, they're not going to get that event. So it's one-to-N messaging, so one publisher, many subscribers. You can dynamically add consumers, so you don't have to know the destination address at compile time or even at runtime. You just have to know it at messaging time. And because as a consumer comes online and says, cool, I want to know about this, here's my address, please send this information to me. If that consumer goes offline and comes back online with a different IP address, it will still get those messages because it's asked for them. What about the messages between the time when the consumer goes offline and comes back online with the new IP address? Okay. So there's, again, subtle nuances there. And if you look at mass transit, and that's a question you asked me a while back, so mass transit physically in a database somewhere stores this type of message goes to this endpoint, so that if the consumer is offline, it still knows where to route it and use the store and forward to get it there, or to attempt to get it there. They've made the assumption the IP address won't change. Okay. Then you've got subscribe, notify. Anyone heard of this pattern? Oh, I think it's the last pattern we're going to cover before we get into the actual distributing portion. So subscribe, notify is sometimes called subscription with gift. I don't know. These are really cool names these people come up with. But the idea behind it is, I don't want to know about all messages of a type. I want this bit of information. So I'm asking you to give me this portion, but it might be a large set of information that doesn't necessarily fit over your messaging infrastructure you're using. So if you're using MSMQ, guess what, you're limited to how many kilobytes you're limited to, I guess, 4 megs, maybe, I don't know. 2 megs. So if you've got underlying technology constraints that are going to limit the size of the messages you can send, but you still want a whole chunk, subscribe notify is what you would use there. So the subscriber would say, okay, cool, I want to know about all of this information, can you please send it to me? The publisher then says, okay, cool, well, here's the first portion of it, here's the second portion of it, here's the third portion of it, and then the consumer has to go and piece all those pieces together to make sense of it. So the example I used was for sending large pieces of information. That's got a clear termination though. So cool, here's the last record. What happens if it's a stream that you're sending and there's no actual termination? How does the publisher or the consumer know, okay, cool, I've got everything now, I can start putting the pieces together? So again, this is a one-to-one messaging pattern. You have to know where the messages come from. And you do, once you've received all the information, you are responsible for what you do with that information. So if you receive the messages out of order, you still need to be able to piece that together into something meaningful. If maybe you miss a message, which can happen, what do you do about that? Do you go and ask for that message again, or do you ask for the entire chunk all over again? What do you do if the consumer goes offline? And what happens if the messages arrive out of order? So halfway through sending, so you've only sent 2 of the 10 messages, and the consumer goes offline. So when it comes back online and gets the last 8, is it going to miss the previous 2? It's kind of application decisions when you implement that consumer that you need to decide. So we've done a lot of kind of sending messages from one place to another place, which is great. Cool. But what would be really helpful, what would be really helpful is if we didn't have to know where we're sending these messages at runtime. So location transparency is a thing. It would also be really cool if we could scale these out. So if I want to add, I don't know, it's taking a really long time to do this billing, maybe I can split the billing in 2 separate processes and have the billing run on 2 pieces of hardware. It would also be really cool if we could throw some redundancy points in there. We could get some delivery guarantees, that'd be great, some load balancing, and what do we do about long-running processes, and also how do we roll back failed transactions. So there's a lot of things that we can add on top of kind of simple messaging protocols. And we've done that as an industry, not we as the guys in this room, but as an industry we have added all of this stuff onto messaging. So if you're dealing with MSNQ, you send in a message from one machine to another machine. That's it. If you're not using MSNQ, so what if you're using IBM MQ? What if you're using RabbitMQ? So all of these technologies have a concept of a broker that they've implemented, or message broker. And the way a message broker works is it's a physical piece of software that runs that sits between the publisher and the consumer. And usually, so the one that I'm going to describe here is the AMQP, Active Message Protocol, Active Message Protocol. It's either AMQP or AQMP. I think it's AQMP. And it's a way of defining what a broker must do. So if you're using RabbitMQ, you'll be using AQMP. If you're using Azure Service Bus, AQMP or AMQ. If you're using IBM MQ, you're still using a broker, but you're not using AMQP, you're using JMS, Java Messaging Services Standard. I don't know. The difference between AMQP, I was going to say AMQP, and I'm going to assume it's right. When you Google it, Google will say, did you mean? It'll be fine. I think I would have actually researched this before. So when you're using AMQP, that is a specific protocol, sort of like TCP/IP. So it's a way of sending messages. JMS is an API standard. So cool, I know you are using Java, so when you want to send a message, you use this API. Then JMS equivalent, AMQP, much lower level, it's a physical protocol that you use. On the IBM MQs, I suppose this is all just a preface to say that what I'm describing here is AMQP, not JMS. Okay. I don't know if IBM MQ works the same either. So a broker sits between the publisher and the consumer. It's usually a dedicated machine or a dedicated server or piece of software running on some type of infrastructure. And inside that broker, it maintains a whole list of queues. So I'm going to represent it with one queue because that's a lot easier to draw in PowerPoint than many queues, and I'm lazy. Publisher wants to send a message, so instead of sending the message to the consumer, it sends it to the broker. Broker then says, okay, cool, I'm going to store this message, and when the consumer says, hey, are there any messages, or I've told the consumer there's a message for it, then I'm going to scratch that message off because now I've delivered it to the consumer. So at a message broker does. It says, cool, I've got a message, I'm going to send it on. So it is in essence a queue if you're doing one-to-one. The difference comes in where things go wrong. So things do go wrong. So if you write a message, cool, the broker says, okay, cool, I've got your message. I will acknowledge that I've written your message. So now you can safely know that I have received it. When the consumer asks for the message and acknowledges that it's received the message, only then will the broker remove that message from the outgoing queue. So it's two-phase commit here again. So tell me you're going to do something, cool, you've done it. Only after you've successfully processed this message will I acknowledge that, and you've acknowledged that you've processed that message, will I remove it from the queue. So, cool. Can you still hear if I talk? Jeez, the false. Okay, so let's say something goes wrong. So we write the message to the queue. The broker says, okay, cool, you want to write a message? Cool, I will store it on the queue somewhere. And before you acknowledge, the producer goes offline. So we're now in a situation where we've written the message to the queue, but the producer, not the consumer, the producer doesn't know that we've physically written the message to the queue. So if you think about databases and you've got your transaction log file, this is a case to the transaction log file, but you haven't persisted it to the actual MDF or replay those transactions. You'd still have that entry. So then the producer comes back online and says, oh shit, here's that message again. We write the message again. We then acknowledge, and the producer says, cool. Yes, we've got two copies of the same message now because the producer went offline. On the consumer side, the consumer is going to go, okay, cool, well, here's my message. Cool, I acknowledge I've written that message off. Message again. Okay, so even though you've got this small piece of software in the middle that's going to do some cool stuff, you need to design your system so that if you get a message multiple times, it's not an issue. Especially if you're using brokers. The brokers are at least once messaging. And this is where that whole concept of at least once and most once comes in. So if you want to do exactly once messaging, it's usually software that sits in the consumer side that goes and tracks, well, one of the message IDs that I've received. Okay, cool, I've got this message, or I haven't had this one before. If you do something like that, though, which is a fairly naive implementation, you're going to eventually store a list of millions and millions of message IDs. And as much as we like to say words are unique, there are collisions that can occur. So you might get a message with a random ID that you haven't had before, but it happens to have the same ID as the previous word. Unlikely, but it could happen. So exactly once messaging, it's difficult to get right. And if you remember from last time, we spoke about ACID 2. You remember what ACID 2 was? Not atomic, consistent, isolated, and durable. It's associative, commutative, idempotent, and distributive. The distributive ones seem stupid. So we're going to say it's ACID. So the idempotent means accept messages, but if you get the same message more than once, deal with it, whatever. So change password as a message. So my customer has now changed their password. If I receive the change password message 5 times, does it actually really matter? No, because I'm just going to update the guy's password in the database. Or if he's changed his address 5 times, does that matter? No, because I'm just going to write the same message 5 times. What about bill customer or debit credit card? I get that message 5 times. Is that a problem? So there's different types of messages you have to decide about. Because you do need to be aware that you could get them multiple times. So that's if it fails on the producer side. On the consumer side, so producer writes a message, cool, acknowledge, we've got a message there. Consumer says, okay, cool, I've got this message, I'm going to go and update this database. Oh crap, I've just updated the database, but I haven't acknowledged that I've received the message yet. Something's gone wrong. I come back online, I take the same message, I update the database again. And then I acknowledge and I scrap the message off. So if you do have the same message twice, either the producer or the consumer side, you do need to go and deal with it. And most of the time it's not a big deal, but if it's things like register a new customer or where you insert in records into a database, it might be an issue there. Or when you're doing stuff like sending emails, you don't want to bombard your customers with 30 emails just because your application had a bug in it and it keeps crashing and then coming back online and doing the same thing over and over and over again. So be aware that things do go wrong, and you do have to design your messages to be in. I don't know if I'm pronouncing that correctly. I hope so. No one's a question for me, so I'm going to go ahead and say yes. So from last time we covered the ASA2 stuff. Very important, especially when you are dealing with messaging systems, because you don't have that guarantee of who one message will only get processed once. And it's important to keep that in mind. And I'm going to say it a lot because it's something that has a big impact on the reliability of the systems. It's easy to say, well, look, I've deployed it in production, I haven't had a single issue yet, my messages just always get there. But what about that one time when it doesn't? And that's the one time that's going to cost Netbank 500 Rand. You're gonna get a pissed off customer because they've been billed twice, or whatever it is. So you do need to be very aware that messages will get there multiple times. Okay, then we're going to cover exchanges. Exchanges are a concept within brokers as well. So the previous examples were also kind of one-to-one messaging. Exchanges are a way of sending messages from one place to multiple other places. And the ones we're going to cover are fan-out, direct, and third one, which I'll remember when it comes up. So a fan-out exchange, again we've got, this is all one broker that sits here. So the exchange is part of the broker. And in this example we've got 2 queues now and 2 consumers. The producer comes in and says, cool, I want to send this message. It's going through this exchange, so it's a fan-out exchange, so every consumer gets that same message. So we would write a copy of that message to both destination queues. The first consumer is online, so it goes and reads the message. When the second consumer comes online, it then goes and gets all the messages that it would have received earlier if it were online. Okay, so fan out, producer sends one message to the broker then goes and sends that message to everywhere else. So this is a good place to use if you want to do things like fault tolerance. What if my data center goes offline? I need to know that there's a high probability that my messages have gone to the second data center, so that we're in a sort of consistent state. You do need to be aware, though, that you're not guaranteed to be consistent. Because if you've sent a message but it hasn't gone to the second data center, same thing with log shipping, you don't know if you've missed anything yet. So that one comes on. Then we've got direct exchanges. So direct exchange is, on the exchange, the broker will say, well, this consumer is only interested in messages that have the root, it's called a routing key, that have the routing key clients. So if I'm sending anything to do with clients, I'll add that as a routing key and I know that it gets to that endpoint. If I want a separate error queue, I might use error as my routing key there. So any errors, I send a message with the routing key clients, it goes to the first queue, consumer can go and pick that off and do whatever it needs to. If I send another message with the routing key error, it goes to the second one. So this is kind of the first place where we've got some type of routing involved. Yeah, everything up until now has been, cool, I've got a message, I want to send it to somewhere, and we know where that somewhere is. With direct exchanges, on the actual broker, you configure, if I've got a message that comes in, and it's got this routing key, it goes out to this endpoint address. So this is not an application piece of code that you'd be working with. This is a broker configuration that you work with. Is anyone yet who's used RabbitMQ? Yeah. For those that haven't used RabbitMQ, it's got the most amazing admin screen stuff to it, where you go and configure right. You can go and do things like your exchanges and your message routing and your high availability. Yeah.
To read that.
Well, I'll cover that just now. Okay, so that's direct exchanges. Then you've got topics. So topics, IBM MQ has got topics, even though it's not AMQP, any AMQP, AQMP exchange or broker also has a concept of topics. And topics work almost like direct exchanges, except you can put wildcards in. So you would create, for instance, a client.star topic and an error or hash.error topic as the topics that you want to create. The difference between a star and a hash in the AMQP space is a star is exactly one wildcard, a hash would be 0 or many wildcards. So if we sent a message with the routing key client.new, client.bill, or client.whatever, it would go to the first one. If we sent anything that ended in .error as the routing key, it would go to the second queue. So something like client.new would go to the first queue, and then client.new.error. So while we're trying to register this new client, something went wrong, it would match to the second queue because it ends with .error. It won't match with the first queue because star maps to exactly 1. A client.new would match 1 once. A client.new.error, that's 2 after client dot, so it wouldn't go to the first queue. As topics are a way of routing messages based off of the routing key, where you've got a lot of flexibility around what that routing key is. Usually when you actually use these messaging systems, you hardly ever, usually when using brokers, you hardly ever directly write in the code to send the message yourself. You would be using something like Nashtrans or NService Bus or whatever the equivalent is in the Java space. And under the hood, something like NService Bus would go and configure the broker for you. So it would, at runtime, go and say, okay, cool, I've got these messages. I know that these services consume these types of messages. So, hey, Mr. Broker, these are where messages must go. These are the routing keys you must use. And whenever you send a message, something like Nashtrans or NService Bus, we go and add the appropriate routing key onto the message that you send. So, what does a typical message flow look like? So we've got 4 applications here, app 1, 2, 3, and 4. And let's just make the trivial assumption that if I invoke application 1 has to call application 2. For application 2 to finish, it has to call application 3, and for application 3 to finish, it has to call application 4. So application 1 eventually has to mean that application 4 has to have been called. So what do we do? So user goes and says, cool, click the button, do the thing, make a coffee. Application 1 would send a message to the broker to say, yeah, I need the result for application 2, please. So the broker says to application 2, hey, can you please give me the result? Application 2 says to the broker, no, wait, hang on, I need the result from application 3 first. So broker goes and says, application 3, give me the result. Application 3 says, no, I need application 4. And then, whoopsie, application 4 gives the result back to the broker, which then sends it back to application 3. Now application 3 can send its result back to application 2. Application 2 then sends its result back to application 1, which eventually says, here's your user output. Pretty awful. We've got 12 network hops here, 12 messages we're sending just so that we can call 4 different programs. So this is, it's an easy trap to fall down into, where you design your messaging system such that you're not passing messages along, but you're physically trying to invoke distributed methods. You're doing remote procedure call. And if you're using messaging systems like this, you're doing it wrong. That is an anti-pattern. Do not use your broker or your queuing technology as a remote procedure call method. As a remote procedure call technique. I don't know. You're going to run into performance issues because 12 messages just to get 4 calls. And sure, maybe it's fine now, but what if you've now got 300 users using the system? So if you are doing messaging and you find yourself doing things like, okay, well, cool, I'm going to send a message, but I have to wait for a result. There has to be a very specific reason why you're waiting for that result. And it comes back to the whole eventual consistency thing. If I've sent the command and I know that command will eventually be executed at some point, do I need to physically block at my code to wait for that result? And it's, like I said, it's easy to fall into the trap of, okay, well, it's just easy if I think in NService Bus it's .register. something, or maybe that's mass transit. But it's where you send a message, and then you've got a callback that happens once you've got a response to that message. Hey, it's easy. The API just works. But you're going to run into performance problems with that. Not during development time, obviously. So what if we, instead of doing a remote procedure call over messaging, what if we actually used it as a messaging system? So we send user input says do the thing. Application 1 says, okay, well, cool, well, application 2, this is my result, but you need to finish the rest of it, so you go, it's up to you. Application 2 then says, okay, cool, right now I've got that, here's the kind of current result for application 3. Application 3 then sends that result to application 4, and application 4 sends the output back. So now we're passing messages along, which is a lot better in terms of performance, because we've now got to work with 6 network hops instead of 12, or 5, 6. Cool, that's great. Do we actually need the broker though? What's the broker doing for us at that stage? And all the broker's doing there is kind of saying, well, I've got this message, oh, it must go over here. Or I've got this message, it must go over here. It's not doing anything fancy for us. So can we maybe drop the broker there? And we can. So in the scenario where we've got the 4 applications, well, why not just send the message directly to application 2? So application 1 sends it to application 2, 2 sends it to 3, and 3 sends it to 4, and 4 does the output. So we don't have a broker here, and what have we lost?
Speed.
We haven't lost speed, we've gained speed.
Well, it depends on where you use it. Who's there? What's reliability?
We've lost reliability. Yes, you have. The broker would handle that for you. You've also lost scalability, yes, because hey, if application 2 is the one that takes a really long time to process, you can't go and throw a new application 2 at the problem, because you've only got one location that you send it to. You also can't change the destination of the message. So I know that when I've got my input from application 2, it has to go to application 4. That's the path the message must take. It can't go any other way. So you've got a fixed path the message has to flow. You have to know the address of every destination. You have to know what your next destination address is. You've now got point-to-point messaging that you're working with. But it is pretty easy to develop. And you can get a lot of speed out of this, because all I'm doing is writing to a queue somewhere. I'm just sending a message. I'm getting messages, I'm doing my thing, and I'm passing messages on. But you don't get to scale with that. What we can do, though, is use a broker as a directory service. So we don't have a broker as an actual intermediary to send messages. We have a broker as more of a location lookup. So as an application comes online, or as each of the applications come online, they then go and register with the broker. And they say, hey, I'm application 1. I'm interested in these types of messages, and this is my address. The broker then says, okay, cool, I've now got to register where you are. And that's exactly what mass transit does with MSF2. That's why I've had that data available. So it's keeping a record of these messages. When they come in, this is the address that they go to. And if anyone wants to send those messages, cool, this is where the message goes. So user clicks the big button that does something. Application 1 says to the broker, broker says go to application 2 and 3 and 4. Okay, so at each stage, the application would either go and ask the broker at that point in time, where do the messages go, or at the startup, as it registers, it would say, well, where do messages go for this type of thing? So you could either do it once at startup, at every message, or perhaps do something where I haven't sent the type of message before, then we go and ask, and I'll cache that locally. What happens when the application is offline though? So we're doing direct messaging with a lookup beforehand, but if the consumer goes offline, where do the applications go at that stage? Where do the messages go at that stage? Because it depends on your underlying technology again. So it should be relatively apparent by now that even though we've got all these APIs that abstract technology away from us, the actual underlying technology you choose to do the messaging with is going to have an impact on how your application performs at runtime. So if you use an MSM queue, for instance, the messages will still go to the destination queue, but if IP addresses change, is it going to go to the right place? And then you might end up having to do stuff to get those messages to the destination when the application comes up. But then ask the broker, hey, so were there any messages for me? It used to be this IP address. Now, if you've got a broker, you can do some cool stuff around that. So the brokers, like I said, you're usually not going to deal with directly yourself. You would use something like end service bus to wrap the broker infrastructure up for you. But if you are in a situation where you have to use Azure Service Bus directly or RabbitMQ directly or IBM directly, it is useful to know that you can do things like broker as a directory service. And you can scale that out. So you can have not a broker, not a single central broker, but you can have multiple brokers for directory service. You can take this all the way to the extreme if you really wanted to. So we've covered brokers, but now I want to start dealing with some kind of long-running patterns that we've got. So has anyone heard of sagas? Everyone heard of sagas? No, you can't. So if you've dealt with long-running distributed transactions, you've probably heard of a saga, and it creates you can brain off when people say that because we've got a pattern that we're going to cover called process manager, process control, process manager, and it's a pattern for dealing with distributed transactions and long-running transactions. So a customer comes and says to the order service, hey, I want to place an order. So place order. The order service sends a message to the broker or the process manager to say order placed. Okay, and I'm using the terminology place order, order placed very deliberately. And you'll see it's going to come all over the place here. The process manager then says, okay, cool, an order has been placed. I need to go and tell the stock service to reserve some stock. So the process manager gets the order placed. Now that this has happened, I need to go and reserve some stock. The stock service then says, cool, I have reserved your stock. So I've been told to reserve some stock, I have reserved some stock for that customer. Once the payment service tells the process manager, so this is now an external component that's put an input in, that says the order has been paid, then the process manager can go back to the order service and say, cool, the order has been confirmed, you will get your item that you have purchased. So the process manager is driving all the decisions around what happens at what stage. If, for instance, we told the order service to reserve stock, and the order service came back and said stock not reserved, maybe there wasn't enough stock, maybe we need to go manufacture some, whatever the reason is, the process manager at that stage could decide, instead of sending a message back to say order confirmed, this is assuming it's been paid for already. Okay. So instead of sending a message back to say order confirmed, we go to the manufacturing service and we say, please manufacture some stock, so that we can then reserve that stock for the customer. So we've got a slightly different path now that has happened because of a different result from a different service. And the process manager is able to make those decisions, it's empowered to make those decisions because it knows what the application logic should be. So once the stock has been manufactured, so we told the manufacturing service manufacture stock, manufacturing service then comes back and says stock has been manufactured. Process manager then tells the stock service, hey, reserve that stock. Stock service says, cool, stock reserved, and then order confirmed. Okay, so the process manager here, okay. The process manager is responsible for guiding the flow of the application. It's a central piece of code or a central piece of infrastructure that determines where messages go depending on the result of other messages. And if something goes wrong, what are the appropriate compensations? And the process manager can decide, instead of sending it to the manufacturing service, it could go to another order, cancel that order, and reserve that stock for the current customer. Maybe it's a super high value customer that's ordered a new mansion out in Kandla or something. So this is typically what is known as a saga if you're dealing with end-service bus or mass transit. And it's not a saga. But it's a very powerful pattern because you can guide and you can control these long-running transactions. If I told the ordering or the manufacturing service to manufacture that stock, I'm not going to sit there and wait for the result to come back and say, cool, I've got it. I'm going to say, just make the stock, and then let me know when you're done. And the rest of the system's going to carry on processing and behaving the way that it would normally, up until I receive a message to say, I've made your stock. Remember the thing you asked for 3 months ago? So you've got a very long-running transaction that you're dealing with here. And it's not a transaction in the typical sense of, cool, well, I wasn't able to persist to the database, so roll back. But there are compensating actions. If I couldn't reserve the stock, what do I do in that scenario? You can tie this up to a distributed transaction coordinator if you want. Please, dear God, don't. So there's another way of achieving this, though, as well. And this is probably one of my favorite patterns, and it's called routing slip. And it's based off of the concept of, well, if I've started a process, I know exactly what the chain of that process is going to be. It's not magic and going to change halfway through. So when you go to Starbucks and you order your coffee, they write all the shit on your coffee cup for you. If you go to McDonald's and you order your thing, there's not someone in the back going, okay, now make a burger. Okay, I need some chips with that. Can I and a Coke? There's no coordinator. Everyone knows what they're supposed to do. They just on their little screen say, okay, I need to make 5 cheeseburgers, and they know up front once an order has been made, it's going to go through these different stations, and it's eventually going to get out to the customer. The way that would work, if you look at our example previously, customer places an order. We don't have a process manager in the middle here. No. So as soon as you place an order, it's an order for 100 pence. 100 pence. I know that if I want to order 100 pence of this particular brand, I know that if I don't have that brand in stock, I have to go to this manufacturer to ask for that, for those 100 pence. Once they come back with those 100 pence, I then know that I can do things. So up front, right at the start, as soon as I place that order, I know exactly where that order is going to go. Even if something goes wrong at every step, I know what the compensation actions are. So I tell the stock service, reserve my stock. So I've got my coffee cup now, I've written there, reserve stock, step 1. After you've reserved stock, tell the payment service to wait for payment. Once the payment service says there has been payment received, then I can go and come back to the customer and say, cool, here's your order confirmed. So that's the happy part. And that's been determined right up front. So order comes into the payment service. Payment service then says to the order service, cool, I've got the payment, and everyone's happy. Now, if something had gone wrong, so there wasn't stock available, well, guess what? I knew up front that if there wasn't stock available, I would go to the manufacturing service and say, hey, order these, or make these things, or once they've been made, let me know about it. So right up front, if something went wrong, I could go and say manufacturer. Once the manufacturing service has made that, or has manufactured that information and reserved the stock for my customer, I can then tell the payment service again. Payment service will go and check, yes, the guy has paid, so now the order is confirmed. And according to the definition of the saga pattern, this is a saga. At every stage, you know, cool, I'm here. If something works, I go here. If something goes wrong, I go here. I know exactly what the compensating actions are. I don't need a central process manager to tell me what's going to happen. If something goes wrong, so credit card declined. Cool, I know exactly where I'm going. I'm going straight back to the UI service and I'm telling the guy to prompt the user to say your card is declined. I don't have to now go and say, hey, where do I go? Because I know exactly once something has gone wrong, what do I do to get back to a consistent state again? And if you combine this with reliable messaging, guess what? You've got distributed transactions without a distributed transaction coordinator or without a process manager. So this is an actual saga pattern. So There's a whole lot of other patterns that are available as well. So the ones that we've covered on the bottom two of the root assistant process manager is a whole lot that we haven't even touched. If you go to being on the recommended reading list, every single time I've done one of these, but it's the Enterprise Application Integration Patterns website. They cover all of these in a lot of detail. And there's a lot of use cases where you don't necessarily think, well, this isn't actually useful for me. But maybe one day when you write a bit of code, you suddenly think, it's almost like I'm doing this. Maybe I can take something that I've read there and apply it to a piece of software that you're working on there. So I do recommend kind of going through all of these. The aggregator, the scatter gather and aggregator are actually very cool, especially if you are dealing with distributed systems. So how do you scale concurrent work out? That has to come back to an answer. If you've got a subledger that's 13 trillion lines long, how do you get what the current balance is if you need to distribute that workload out? So there's some very cool stuff you can do there. So the question then becomes, should you use messaging? And I did that on purpose, but it's the wrong question. It's not should you use messaging. Chances are you already are in your applications. Maybe you're just not really aware of it. So messaging happens at different levels. You've got the physical transport. That's cool. Then you've got your application design. So if you designed your application to be loosely coupled, you've got some components of messaging there, even if you're not physically sending a message over a queue. If you maybe use an event sourcing, if you're really cool, then your entire system is based off of messaging. Your entire application design is based off of messaging, and maybe you just don't even know it. So the question isn't should you use messaging, the question should rather be how can understanding some of the patterns around messaging that go further than just point-to-point messaging, how can understanding those patterns make my application perform better? Or how can I exploit some of the underlying technology that I'm using in order to get more scalability or more reliability from the system? There's some recommended reading at eaipatterns.com. That's AMQP. There it is. I did actually research it. AMQP. So, yeah. What do you guys want to cover next time? Any suggestions or any specific requests? Good. Are there any questions on this stuff, by the way, before we get into the next time? Let's check the handout, guys. Okay, well, if there's no questions, DDD, NoSQL, event sourcing, Akka model, super. Anyone heard of Akka? Golang? Need someone say Akka model. Yeah, so DDD next time. Native and design. That's where you deal with your bounded context and the aggregate roots. Okay, so DDD. Cool, thanks guys.
Yeah.